You can use a certain force, okay, in some direction, and thus you are going to do work, okay? You gotta eat something to get that big out of the room, for example. Other than that, we have STEM week running, okay? STEM week, and on STEM week you get 10% off the whole brand new nonlinear dynamics collection, so make sure to check that out too. A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians! Welcome back to another video. My throat's still hurting, but I'm trying to do my best I can at least talk at this point. I'm doing some physics today. I have suddenly decided to do some more physics because I have a bunch of stuff I want to do regarding physics, especially classical mechanics. Bit more stuff, and hence I wanted to go ahead and do some Lagrangian mechanics today of a problem that we have covered already like 2 years ago. It was about the rope sliding down table. You can find all the referenced videos down there in the description somewhere at the top, okay? And what is this problem about exactly? Let us do a little tiny little sketch, okay? Now, suppose we have a table, and on this table we have a very sexy snack lying on top, okay? It's a rope, and this rope is going to hang down, okay, from the table. And what is going to happen to snack if snack decides to hang down a tiny little bit, where snack is going to slide down more and more up until snack falls off the table, okay? Poor snack. And this is what we want to find out today. What is the differential equation which kind of dictates how this system with the rope works? And for this, just one more information. The part that is hanging down, okay, from the table is going to be called x, and we're going to extract way more information from this tiny little x that we're having here. But before we get into the actual video, I would like to thank today's sponsor, The Rich, for sponsoring another video here on this channel. This right here is my nice little Rich wallet, and I love this thing. Using it all the time because it's so nice and handy. It's so small, it doesn't even bulge in your pants. If you are like me and you love to have stuff for ages, and if you really like stuff to not break, then the Rich wallet might be the perfect fit for you, because they promise you that you are going to never need another wallet ever again. You're going to get a lifetime warranty on this little thing right here. It comes at a certain price, but it's definitely worth it. And to check it out, you can use the link down there at the top of the description. So recently I decided to give a few other products from their website a shot, and hence I decided to buy myself the Rich backpack. This right here is the weatherproof version, and I gotta admit, I love backpacks. I have a lot of backpacks at home, but this one is by far one of the best I have ever owned. It has a lot of space where you can put stuff into. It's completely weatherproof. I was walking around in the rain with it, and my Asus ZenBook Pro Duo, which is highly expensive, was still alive here in this very soft pocket, in this very soft space. Other than that, you can charge your phone using this built-in phone charging cable that you are going to have here, and it has a lot of other functionalities like a lot of zippers, and you can keep all of your stuff safe. Just like the Rich wallet, this right here was an absolutely perfect buying decision, and I do not regret it in the least bit. You can find it down there on their website too. So if all of this feels like it's something for you, make sure to check out the link at the top of the description. With it, you are going to get 10% of your whole order, as well as worldwide free shipping. Use the code PapaFlammy at checkout, or just the link rich.com/PapaFlammy, and you're going to be redirected to my personalized offer here for this channel. So try it out and support the channel this way. And now we are going to dive into the main video. Now we are going to take a look at how Lagrangian mechanics actually work for something like this. And this is one of my most favorite problems for Lagrangian mechanics ever, because it involves a few technicalities that you need to take care of. It's kind of fiddly squiddly and not too easy to handle, just like with most Lagrangian systems. So if you're not familiar with this formalism yet, what you want to do is we want to find out the so-called Lagrangian. It's some kind of energy. It's the difference between the kinetic and the potential energy. And then we are going to solve the Euler-Lagrange equations. Those are just set of partial differential equations where we can plug our Lagrangian into, and then it's going to spit out our differential equation, which is going to dictate how this system works. So the first thing we are going to take care of is the kinetic energy, because that's most of the time the easiest thing you could possibly deal with. So what is going to happen with the kinetic energy? So the kinetic energy in a normal case looks something like this. We are going to have the mass of our object divided by 2 times the velocity. So in Lagrangian mechanics you're going to have a vector in some way most of the time, and this thing differentiated pointwise and then squared. It's basically just a scalar product of the time differential of the certain vector. And now we just need to find out how our mass is moving all the time. In which direction is it moving all the time? Now, what is the mass that is moving overall? This is something that you might want to keep in mind. The mass that is moving overall is the whole mass of the object. I mean, if this part down here is moving downwards, then this part up here is also going to move. Overall, the whole mass of the object is going to move in a certain direction. Okay, so our mass m is just going to stay. As being our mass m, we have to do some more work on u later when it comes to the mass. So it's not that easy. This is why I explained it a tiny little bit right now. Now, what about our displacement exactly? What about our r vector that we're having? Let us construct our r vector and see how it actually looks. I mean, our r vector is just going to be the position where our mass is going to be all the time. Okay, you can interpret it like this. Now, we are going to take a look at this problem this way. How is our rope sliding all the time? Overall, our rope is only sliding in a certain direction, downwards, into an x direction, okay? It's also sliding up here, but the whole concentrated mass is basically going to slide downwards towards Earth in some way. Meaning, what is the direction that is going to be taken by our mass m, by our rope overall? Our rope is going to go downwards into the x direction. Okay, we have a weird coordinate system here. It's going to go downwards in the x direction, and we do not have any other movement with regards to the mass. Let's just imagine we have a point mass down here, hanging there, having all the mass of the rope on there, and this is how it's going to move. Okay, just imagine it like this, meaning it's just going to move downwards into the x direction, and other than that we don't have any other coordinates that are going to act on our kinetic energy. Okay. Now, one thing that you should keep in mind is that our r vector is going to kind of be changing over time, like the x component. Just imagine it with snack, okay? Let's say at this point in time our x component is only going to be at 1, for example, okay? Now snack slides down a tiny little bit more, now it's at 2. Slides a tiny little bit down more, now it's at 3, etc. and so on. Meaning, over time, our length that is going to be hanging down is going to be time dependent. It's going to change over time. The length, the part of the rope that is hanging down the table is going to change over time. So x is actually with respect to t. And this is really important because we now need to differentiate our r vector that we're having here. Differentiation of vectors works pointwise, meaning we are just going to differentiate x with respect to time, meaning it's just going to be x dot overall, and all the other ones are just 0. Now we are going to take the scalar product of the vector with itself, leaving us overall with a kinetic energy of m over 2 times x dot squared. And hence we are done with this. Okay, now we can go ahead and take a look at our potential energy. Potential energy is a bit harder to handle in this case. You can approach it from 2 directions. You can either say that your gravitational force, this is the only force acting on our rope, basically, the gravitational attraction of Earth. Our gravitational force is going to be directed downwards, okay? Meaning we are going to have a negative potential energy, but negative potential energy should also ring a bell for you. The negative potential energy of a system is just the work being done by the system, basically. Meaning there's another approach you could take on this problem, namely that our our potential energy is nothing but negative the work, or the work is nothing but negative potential energy, okay? It works both ways around. But now, what is work exactly? Work is being defined as the force being done over a certain distance, over a certain displacement, okay? So meaning I can use a force and let it act on my wife, for example, smash her against the wall, for example. This is something you can do, but it also has a certain direction. It's a thing that changes with vectors, with the angle that our force is basically acting on another object. Meaning, how can we put this into mathematical terms? In mathematical terms, we are going to have an integral from one position, so from the initial position to the final position, okay, of our force F that we are going to apply to the system. In the scalar product with the infinitesimal, I'm going to call it R for now, basically the direction, okay? Meaning, what we are basically doing, if we have a straight line, then the force, then the work is really easy to calculate. But if we have, for example, like this direction, okay, like a force doing it like this, we have to compute an integral because we have to take infinitesimal small little r's, okay, and then we are going to add them up, infinitely many of those, resulting in an integral. This is just how you derive the work, basically. But there's another formulation for the scalar product, namely the scalar product can be interpreted as being nothing but, okay, we are going to take the magnitude of our force F, we are going to multiply it with the magnitude or the norm, but right here it's just the magnitude, okay, we are just going to take a look at the Euclidean norm, the norm of our basically infinitesimal, times, and now we are going to have this angle part. We are going to see how our force and our infinitesimal, our direction, stand in a certain angle. What is the angle being enclosed by those? Okay, so we are going to have the cosine of the angle between our force and our infinitesimal. And really doesn't matter if the cosine is inside or outside the integral, because this right here is just going to be a scalar overall. This is just what's going to happen, okay? Because this is just the dot product. It's going to spit out a scalar overall. Now, here's the thing. In a normal case, our work being done is going to be done by the whole rope. But only part of the rope actually does work. Let me explain for a second. If I move on a horizontal path, okay, it's a conservative force, we say, then my work is going to be 0. And here's the reason why. So the only force acting on myself, so just imagine this part being me right now walking because it's lying flat on a table. Now the force acting on me is just a gravitational force. It's going to be downwards directed. Now I'm moving in this direction or this direction, really doesn't matter. Meaning I'm going to move basically parallel to the floor. Now what are we having? We're having a force which goes down here and we are going to have a direction going this way. Now what is this angle? That's a 90-degree angle. And what is the cosine of 90 degree? It's going to be 0. Meaning the work being done by this part up here on the table is going to vanish. So we only really care about the work which is going to be done by the part hanging downwards, okay, off the table. Now we need to find out what the angle between the force acting downwards and our direction in the downwards direction is, and that's really easy to find out because we're going to have a force which goes downwards, and parallel to it we are going to have our infinitesimal also going in the same direction as the force does. Now what's the angle between two parallel lines? I've made a video on flammable maths too about that, kind of. It's going to be 0 degrees. So we are going to have the cosine of 0, and the cosine of 0 is just going to be 1 by definition, okay? Because the cosine of every argument is just 1. Meaning we are going to be left with negative the integral from t1 to t2 of, we are going to have a certain force. This force is going to be the gravitational force, but beware. Here is where my argumentation comes in with only the force acting on the part that is hanging down the table. It's going to only act on a portion of the mass of the whole mass. Meaning we are going to call this new mass capital M, for example, okay, times g. Okay, M times g is just our gravitational force. And now we are going to have the absolute value of our dr. There's a vector arrow missing. So what's the absolute value of dr? Well, speaking in the terms of our problem, our r vector is just going to be the x component, meaning we are going to integrate with respect to x. Now we must be really careful with this. If you just were to integrate this, you are going to get m times g times x, but this is wrong because our m is actually with respect to our time-dependent variable x. And here's why. So we are going to take a look at just two scenarios. Let's say that the total length of our string is going to be 6 meters. Okay? Capital L is 6 meters. Now the length of this rope is going to stay constant all the time. Meaning it could hang down, let's say 2 meters. Okay? And there are going to be 4 meters left up here. Meaning our delta, not our delta x, our x with respect to t, is nothing but 2 meters in our case. Now, what is the mass that is now hanging down off the table? Okay, so if 2 meters are hanging down and we suppose that the mass is being uniformly distributed along the whole rope, then that means, okay, 2 of 6 is 1/3 of the mass is only hanging down. So meaning our capital M, our mass that is hanging down, is going to be 1/3 of the total mass of the object. Okay, to put this into different terms, this was 2 out of 6 meters times our mass M. Now we can put this into other terms. Okay, notice 2 is going to be our x that we are having here, meaning our M is going to be our x with respect to t, divided by, and 6 was the total length of our string, times M. And this is exactly how we need to do it. Our capital M is going to be composed of x divided by our whole length times M. And this is what we are going to plug into our integral. Now we are going to get that this is the integral from, okay, now we can plug in upper and lower bounds. Now let us suppose that our x starts up here, meaning we are going to have a displacement starting from, okay, 0. Basically, if you imagine a coordinate system being in here from 0 up until, okay, our x with respect to t. This is just our length that we are going to have down here. Okay, this is just where our point mass is basically going to hang. Our work is just going to be over a certain distance, and the distance being done by sliding down is just x. Okay, in our case here it would be 2 meters, for example. Okay, this is x with respect to t. Now we are going to plug definition for m in. This is going to be m over L times g times x, integrate with respect to x. I'm terribly sorry. And this is really too easy. And this is really easy to integrate. Namely, this is going to be, okay, negative x is going to be integrated x squared over 2. So m over 2L times g times x squared from 0 to x with respect to t. Okay, and now we are basically done. At 0, this is going to vanish. This is just a polynomial without a y-intercept, basically y-intercept. And in our x, we are just going to plug in x, leaving us with negative m over 2 times L times g times x squared, being hence nothing but our potential energy U. Now we can plug all of this in our Lagrangian, meaning our Lagrangian is hence nothing but our kinetic energy, m over 2 times x dot squared. And then negative, and negative is going to become positive overall. Positive. Now we are going to get m over 2L times g times x squared. This is our Lagrangian, and now we are going to plug the Lagrangian into the Euler-Lagrange equations. What are the Euler-Lagrange equations? You might ask yourself. I'm going to write them out here. I made a collaboration with Vivek once, so v cubing x. So check that video out. Link will be also down there in the description. This is just a differential with respect to our constraint. Our constraint is the only time-dependent thing that is changing over time in our system, which is x in our case. So we are going to differentiate partially our Lagrangian with respect to x. We are going to subtract the time differential of the partial derivative of the Lagrangian with respect to the time derivative of our constraint, so x dot, and this is going to give us 0 overall. Yeah, it's a mouthful. I never know how to really say this line right here. But overall, this is really easy to compute. Let us start with the differential of our Lagrangian with respect to x. Okay, it's with respect to x. Please keep this in mind. It's not with respect to t and not with respect to x dot. Meaning, this part is basically being treated as a constant, and we only need to differentiate this right here, leaving us with m over L. 2 and 2 is going to cancel out, g times x. Now what is the time derivative of the partial derivative of the Lagrangian with respect to the time derivative of the constraint? It's going to be the time derivative of. Now, if we were to differentiate the Lagrangian with respect to x dot, okay, then this part is going to vanish. This right here is just a constant with respect to x dot. Now, what is going to happen here? We're going to drag the 2 down yet again. This is going to give us m times x dot. And what's the time derivative, okay, of this part? It's just going to be m times the acceleration x double dot. And now we can plug all of this shit into here, leaving us overall with m divided by L times g times x minus m times x dot being equal to 0. Now we are going to suppose that the mass is not equal to 0, everything else would just be absolute bullshit. We are going to divide both sides by m, leaving us with a differential equation of being g divided by L times x minus x dot is equal to 0. Meaning the velocity is nothing but g divided by L times our displacement x. And this is the differential equation that we can easily solve, and you can find a solution down there in the description somewhere, being the original video of the rope sliding down table. I hope you did like this explanation. I tried my best. I think physics videos are kinda hard to record because you have to talk quite a bit to explain everything nicely, but I hope you still did enjoy this video. Don't forget to check out The Rich, because they actually have some very good products on their website, and I'm so satisfied with both of those. So seriously, check them out and support channel this way. Other than that, we have STEM week running, okay? STEM week. And on STEM week, you get 10% off the whole brand new nonlinear dynamics collection. So make sure to check that out too. And other than that, I wish you guys a flammable day. Subscribe to Flammable Maths too. Now I'm going to kind of spare my throat, okay, for the rest of the day. And until the next video, I wish you guys a flammable day. Ciao!